the function f of one if f of x f of y minus x y. So what this means is two different inputs give different outputs. Actually, I think that maybe a good way to start off is with a non-example. Can anybody give an example of a function that is not one-to-one? So there's two different inputs that the function will give the same answer. Can you think of a function where you put in two different values of x, but those two different values of x give you the same value of y? Actually, that's absolutely correct. Her function is f of x equals 1, right? What happens when you plug in x equals 1? You get 1. What happens when you plug in x equals 7? You get 1, right? In fact, no matter what you plug in, you get 1. So that's about as an extreme of an example you could possibly get. How about this? Here's one that's sort of our old-fashioned friendly neighborhood parabola. So can anybody give two different x values in the same y value? I think that's supposed to be the same budget a little bit. Right? Two different inputs get the same output. So can somebody look at this picture that I've drawn here and tell me what's the test that you associate with one-to-one? Yeah. Horizontal line test. How many of you have heard that? That's no buzzword. Well, this is why the horizontal line test works. Because notice I can draw a horizontal line through here, and it hits the function, it hits the graphical function in more than one place, right? That means where the horizontal line hits it, there are two different x values in the same number. A function is one-to-one. A function, you see calculus from RR, the graph of y to f of x passes the horizontal line test. And what does it mean to pass the horizontal line test? It means you can't pass a horizontal line through the graph and have it hit the point. Okay. Now, what's the big deal about one-to-one functions? Yeah. Is one-to-one with domain AB in range CD. Let me call this something X. Then inverse. With domain CD and range B. Right. Whoops. And we be more specific. What does it mean to be an inverse function? Well, it means that f inverse of f of x is x. So if you take some number, x, and you plug it into the function, then you do the inverse function, it gets you back to where you started. Inverse functions are the reverse. Think of those sort of keys. This is true for all x in the interval A to B. And A to B is the domain F. And F of F inverse x is also x. So it converts on the other side. What's my appropriate range for x here? Exactly, C. Because I'm plugging in x to F inverse, which has domains. Let me kind of draw you a picture of this, and we'll look at maybe some familiar examples. F inverse is like a mirror image. It takes domain and range and inverts their role, F inverse. And they undo each other. These functions untie each other in both directions. Okay. So, right, we can draw a picture of this. Now let's suppose, and I have, let's see, I better make this point. Go to, let's suppose this. Say this is x. Now notice that what these equations mean is notice that if y is f of x, then if I put f inverse here, f inverse y is f of f inverse x. So in other words, what this means is if point AB is on graph y is f of x, then blank is on graph y is f inverse x. It's both. But notice, if this is B, and X is A, that means AB is on the graph of that, right? But now, this is B, and this is A. That means BA is on the graph of F inverse. So again, the inverse versus the order. So, if I were to draw for a tangent point, the inverse, then this point right here, the fact that you have 0, 2 on the blue graph of f of x means that you must have 2, 0 on the graph of f inverse. Since you have 3, 5 here, you must have 5, 3 here. And for every point along the way, it's got a mirror image down here. So actually, I didn't involve this very well. It should come up on this. The inverse should look something like this. So it's a reflection around the line like that. But okay. Now there's a concept up here. If you have AB here, and the slope of the tangent is here. Suppose you have AB here. Yeah. Then you have BA here. Anybody want to take a guess as to what the slope of the tangent line is? So at this point here on the original function, the slope of the tangent line is 10. Here you've got BA. What do you suppose happens here? The same way. I don't, because it looks like this one's a little bit flatter. This one looks steeper, doesn't it? Let's see if we can find out. I'm gonna actually figure it out. Maybe this will help. I'm actually gonna find. So let me belay this question. Maybe we can figure this out. By the way, what's the easiest kind of function to find a tangent? Somebody can be smart on the answer. Right, how about just the line itself, right? Right, because if you have a line, it is its own tangent. I agree with that. So let me start off with this. Finding. I'm going to give you a procedure finding inverse functions. This will work if function is 1-to-1, that is, if it has an inverse function. Right? This procedure always works theoretically, but actually solving is incredibly difficult. So for some functions, it's not practical at all. But if you have so it has an inverse. So it's 1-1 on symmetry, so it has an inverse there. Then number one, see if I remember this procedure of what you did. Good. Switch X and Y. So now you got X, left Y. Right. And now what? Good, good. So you all been down the road. That's good. When you solve Y, you get everything. Say, the problem really is with this step right here, because it doesn't take much for me to give you an equation. It's just really you're not going to solve it. However, there's a lot of functions that you can solve, and I'm going to give you some examples here. By the way, can anybody think of? So we know now the inverse function, or I'm sorry, 1-to-1 functions have inverses. Can anybody think of a large class of functions that are 1-to-1? What you think about? You think of a large group of functions that pass the horizontal line test? Linear? Absolutely, with one exception. There's one really bad fail for that. Anybody know what it is? What's a linear function? Well, I should say, what's a line that passes the horizontal line? A horizontal line itself, right? But as long as your slope is not 0, you're good to go. Do I agree with that? So let's just take something like this. So example, let Y equal mx plus b with m not 0. So here I'm saying that I'm gonna take some line, and it's not horizontal. Fine. If I call this f of x, I want to find f. So there's my step one, where I switch the roles of x and y. And now notice I can solve for y. Notice it's important that m is not zero. If m is zero, I'll just get x equals b and solve for y. Suppose the slope here is m. And now flip this thing over, and now this tangent line will be a. What is the slope of this? 1/n. Right, because this line and this line should be inverse functions. Right, because this tangent line is a reflection of this around the line. Yes. Well, that's what I did, right? Because I took this right here and exchanged the y and x, and now just solve y. This would be the inverse function. And let me actually show you that this works. So then we'll do another example. So we have f of x equals mx plus b, right? That was our original. And my wild plane is f inverse of x is 1/m x minus b over. Right. Check it. And here's what you can check. Let's look at f inverse of x. This is an f of 1/m x minus b over m. Okay, so far. Now, I'm doing f to this big blob. And what does f do to a blob? It multiplies it by m. M times my blob. And then it adds b, whatever result later, right? See what happens. This becomes x minus b plus b, which is x. There we go. So it inverts the function. Start with x, do it, then plus f, get back. Check it the other way. I do f inverse of x. Faith, did I address your concerns there? Okay, let's do it now. Let's get the number. How about this? 2x over 3x minus something. That should be. By the way, you must check this out. See. So y is 2x over 3x minus 4, right? Okay, step one, reverse the roles, x and y. And now just try to dig around with this and solve for what y is. So I don't know about y'all, but I hate fractions, so I'm gonna multiply both sides by 3 minus 4. course, on the right side, they'll let you know. So let's see what this gets me. This gets me like 3xy minus 4x equals 2y. When I multiply through on the left-hand side of the equation. So I'm trying to solve for y, so I guess I need to isolate y. So let's do this. Let's bring the 2y over here, minus 4x here. So I get 3xy minus 2y equals 4x. So I get y times 3x minus 2 is 4x. And so I get y is 4x over 3x minus 2. And if you do F inverse X, you should back that. So you can always check me. Okay, any questions? Okay, so this is, how many of you remember this maybe vaguely from back in the days? This is what I want to know. Well, you've got all these inverse trig functions here, right? And the only one that doesn't really puzzle the crap out of me is the inverse tangent of this line. I'll tell you why. Well, actually, that one puzzles me too. Here's the problem. You have you've got 6 inverse trig functions, inverse cosecant, all that fits. Can somebody tell me what sine x is? That's right. If you're an engineer, you're going to see this business all the time, right? I remember like something. Yes. Two. 2 minus power 2. Now, there's one thing, since I'm talking about inverse sine here, that ought to probably boil your blood a little bit. What kind of functions have inverses? 1-to-1. Let me ask you this. Does this thing pass the horizontal line test? No freaking way. How in the world do we 1-to-1? Can somebody tell me what the problem is? And why is there a horizontal line? What happens if I take this whole animal and try to take the inverse function? Right? What happens if I reflect this around the line y equals x? What's that horizontal line turn into? If I revolve this thing around the line y equals x, what happens to that horizontal line? It comes what? Vertical. Do I agree with that? So if I reflect this around the line y equals x, that horizontal line will now be vertical. And it will be piercing this new drawing I have in infinite places, right? So when I evolve this from line like x, it's no longer a function, right? Because it fails very badly vertically. That's how the horizontal and vertical line tests are related, right? If this passed the horizontal line test, when I flipped it over the line y equals x, it would pass the vertical line test, right? And it would be a function. Problem is it's a function. So where in the world are they? Is this a big red herring? mean, where do we get these inverse trig functions? We have something that's not even 1-to-1. Here's the idea. The idea is you can capture the theme of sine only by knowing a little bit of it, right? If you know what one hump does, then you know what everything does, right? Because the sine is periodic, right? That's a big thing about trig functions. They repeat every 2 times, right? In fact, some of them repeat quicker. Right? Okay with that? So if you know what one hump does, you're good to go. So what they do is they take sine x from here to here. And they say, forget about everything else. So the way they do inverse trig functions is you restrict sine x to domain minus power to power. Now, just the red bit is 1. Everybody agree with that? Because you can't pierce that by horizontal line. Everybody agree? Now just take this. So for example, this is point power to 2, 1. This is point minus power to minus 1. And you get the inverse sine. By the way, what does it look like the slope of the tangent there is? Right there. Yeah. Looks like 0, doesn't it? Right there. The inverse sine, and I'm sorry, I'm very good at this. When you revolve this, so now you've got the point -1, negative power to 2. And you've got the point 1 power to 2. And it actually goes like this is what y equals sine x. The domain -1, 1. Take the number 2 and put it in your calculator, press the inverse sign, it'll give you an error, right? Because the domain is here. And the range is minus power to power. By the way I've drawn my beautiful picture. Does anybody remember what we did this last time? Anybody remember what we came to? Okay, I see. Okay, the domain. Well, the domain goes from -1. What does it look happens to this when x is very, very close to 1? What's happening to the derivative? It's actually very close. Numerator always 1, right? Denominator getting very, very close to 0. Always positive. What's happening to the derivative? Very, very close to 1. It's getting infinitely stable. Everybody agree with that? This is going to infinity. And look at my picture. See the 0 slope. Getting closer and closer to 0. Right. Same down here. So that's kind of a good gut check. Let's look at one more picture. So for example, tangent. Everybody agree this is what changed next week, and there's copies of this, right? You just, it's like a copy machine. Over and over. Agree? What happens is, instead of looking all tangent, because it's just copies of the same over and over, you just look at this piece. This piece by itself is one. Everybody agree? with me? So you take the domain minus power to power to. This time not including the input, because you can't plug in power. And the range. Look at the graph. Can you tell me what the range is? It's everything, right? It doesn't matter what real number you have, there's some Y coordinate, right? It's all of the real numbers. What is the inverse of tangent? Well, the inverse tangent. I can actually use these vertical asymptotes to help me out. Because when I brought this around the line flex, these vertical asymptotes have to be horizontal. So it goes like this. And I said that derivative of this. What happens to the derivative of the inverse tangent in x is very, very low? What's happening with this derivative? This one, the derivative of x is very, very large. What's this going to? Good, it's going to zero. And this is exactly what my picture reflects, right? As I go out here, it looks like it's getting flatter and flatter, right? Same in this. And it looks like the biggest activity of the circle is when x is 0 or 1. And I'm going to do kind of a new one. I'm gonna draw the inverse C. This one's actually a little bit tricky, but this, I think if you kind of understand this is really good. Secants like tangent since every 5/2. Yes. So it's got a vertical asymptote where the cosine is equal to 0. So what the secant is actually going to look like is, notice between minus power 2 and power 2, this. Because in this range, the cosine is positive, right? And between here and here, this is 1. 0, 1. And then this range here, when power 2 and 3 of power 2, the cosine is negative. This point, pi negative 1. And it does this magic over there. Minus pi. Now here's the problem. I took that piece of tangent middle, right? Because it's 1 to 1. I can't take this picture and see it, right? Because it's not 1 to 1, right? It's the horizontal line, right? So I've got to pick my poison, and I've got to check my notes here, make sure that I pick this right. Yeah. So here's what I'm going to get. I'm gonna draw it in red. I'm gonna ignore everything except the part in red. I am going to do this. And this should capture the essence of secant, right? Because I've got sort of an up part and a down part, right? I agree with that. So let me kind of redraw it. So I'm going to forget about all the secant except for in this range. So this secant actually here goes from 0, 1 to power 2. And then we can go. This is going to be my y secant x. Everybody good with it? And that piece is 1 to 1. Now, let me draw what the inverse is. Now, the inverse secant is what I get when I flip around the line of y equals x. So, actually, it always helps me kind of get. So I know that I should have this horizontal axis over here, over 2. Okay, so that should be a player. I should have a point -1 pi. So let's see, -1 pi. And I should have a point 1, 0. And so it looks to me like this thing. This. This is what inverse secant is. By the way, what can you say about the slopes of the kingdom? They're always positive. Right? It looks like this is going to be y secant inverse x domain. Domain is all x is greater than or equal to 1 in x, right? So what this means is everything 1 and beyond, everything -1 to the left, right? Every x. Because notice 0, for example, is not in there, right? And the range. Like range. Looks like it's 0 to pi, except what? So the range goes from 0 all the way to pi. There's one thing that's not correct. So it's like you took that interval from 0 to pi, just pulled out the dot out. What is the derivative? Well, so y is secant of x is still the rest. Yeah. Secant of y is equal to x. Everybody agree with that? And what's the ddx? Again, anybody remember what the derivative of secant is? Okay, so the derivative of secant y is equal to y. Am I done? And derivative of x. So I get 1. I'm sorry, I get y prime is 1 over secant y tangent becomes well. Now, secant y is x. Right? So I can adjust this a little bit. Now, what about tangent? I like to get that points. How about this? Let's use. Remember that identity, tangent squared plus 1 secant. So and I'm tempted to write 1 over x times radical x squared minus 1. That's not quite right. Somebody pull me by the subtle point. Notice that we have 2 branches here. I get this species. Now remember, this is supposed to be tangent y. If you're on this piece of curve, what can you say about the tangent? Notice that your y coordinate is 0 and pi over 2. What can you say about the tangent of y? Just sine, S-I-G-N. So this is basically the first quadrant, right? This is true about the tangent. It's positive or negative? It's positive because in the first quadrant, the sine goes positive, it's positive. And if in this other range, then the tangent of y was tangent in the second quadrant. It's negative, right? So what do we get? Well, we get actually this is 1 over x times tangent y. Yeah. And this bit is negative, I'm sorry, positive. And 1 over x tangent y if and this time it's negative. So this is equal to 1 over x times the square root of x squared minus 1, because that's what tangent is. And 0 to pi over 2. And it's 1 over negative x square root of x squared minus 1. And 0 to pi over 2. Why the negative? Because now the tangent of y is negative, and that square root that's supposed to represent it is already positive. But notice in this range, x is negative, and in this range, x is positive. So I can collapse this the following. Notice our observation at the beginning. Remember how all tangent lines have to be positive? Right. And notice this formula gives you exactly that. Whether x is positive or negative, you get a positive. Right. That was a little bit tricky, and I will tell you, and this is one of the reasons I did this problem. In your book, they give you this formula. In the calculus book that we used to use, Stewart book, gives you a formula that doesn't have the absolute value. Is Stewart wrong? Stewart wrong is the only possibility because I derived that. Why does Stewart give a different answer? Because Stewart used a different definition for the secant in the inlet. In the Stewart book, they use this piece and this piece. So instead of the two reds, they use this red, green, and this piece. They use those pieces of secant. You might try to go through that and see if you can work through it and show that if you use these two green pieces to find the one-to-one part of secant, and then you do all we did, instead of the absolute value, you'll just get a simple formula that you see in the Stewart chart. Any questions? Okay, I'm going to give you all the theorem now. We're going to talk about inverse functions that you work with it. In your book, I think I've given you most of these. I didn't give you the derivative, the inverse cosecant, things like that. You can find that in your textbook, or pretty much anywhere. As far as being smooth for the test, let me make the following recommendation. People always say, "Oh, what do we have to know?" Well, one of the things I dig about math is you don't have to know anything. You just have to understand it and drive what you want. Now, it's practical. You don't want to do that on a test, right? Too much, right? From a practical point of view, it's probably good for you to remember to be correct, the derivative of the inverse tangent, the inverse sine. The other stuff, let me put it to you this way. The other stuff, it's either not going to help you to remember because I might ask you to derive it, or I would just give it to you. But remember the derivative of the inverse tangent, inverse cosine. Okay. So I'm going to actually give you a theorem here, and then I'm going to give an example that you show how to use this. Let f of x be differentiable and have an inverse, so that that's an inverse on so just some interval like 0 power 2, something like that. If A is in I, so this is some number in I, and f prime of A is not 0, then f inverse is differentiable at B f of A, and G prime B is 1 over. This looks like a bunch of gobbledygook here, but really, let me show you what this is all about. String. Suppose I have a function here. So suppose this is A. So this is point AB. Why is that? Now the inverse function. Oh, yeah. And here. The inverse function is something like this. And it has point BA. Right. So here we have A, D, A, B. Now, what this theorem says here is, let's see, A is an I. Okay, so here's the interval of definition. This A is in this interval. It's got an inverse that's 1 to 1. Does it look to you like f prime of A is 0? So it looks like right here with the incline 0. No, it doesn't. So this is has some slope that's not 0. What this says is the inverse function, this one here in red, is differentiable at B. So it's differentiable right here. And the derivative or the slope of the tangent here is actually, and unfortunately I drew this using the slope of 1, but this should be G prime of B is 1 over F prime. So for a more dramatic example, if I took this here steeply, and I took the corresponding here, which is flatter, these two should be, these slopes should be the same. This is essentially what this theorem says. Here is essentially why it's true. I'm not trying to make your life worse. I'm just saying G of X is F inverse of X, just so I'm going to take a derivative of this, and I don't want to take F minus 1 prime. It's confusing. So this is just an alternate name, right? F inverse is its real name, and we just call it G for a name. Y goes to B, G, Y minus G, D over Y. But see, G of Y is equal to X, and G of B is A, because G and F are inverse functions of each other, and Y is F of X, and B is F of A. Now, I no longer have Y's and X's, but as Y goes to B, as Y gets very close to B, the X gets close to A, vice versa, because these functions are differentiable. and this is limit as x goes to a of 1 over f of x minus f of a, f of x minus a, 1 over f as we picture. Okay. Any questions? Okay, so let me do a follow. Okay. By the way, so let me kind of bounce where it's from here. First of all, to apply this theorem, I need to know that my function is invertible. All right, and this one does. Anybody tell me how I don't want any kind of weird weighting function that maybe is a vertical. This is something we're actually going to get to. But let me ask this, and I want to leave the derivative. What's the derivative? Gotcha. Agree. Okay, so this thing tells you what the slope of the tangent is to this function at every point x, correct? What can you say about the kind of numbers you're going to get out of this derivative? Right. In fact, what's the smallest you could ever possibly get? 1. Everybody agree with that assessment? I agree with that. Right, because these are all even powers, so that means, however I draw this function, the slopes of the tangents are always going to be at least 1, perhaps a lot bigger. Can somebody tell me what that means about this function? It is going up, right? Everybody agree with that? So I'm not going to be able to go on that, but it doesn't matter. Let's see. Oh, it's 3 at 0. And of course, at 0, it's got a slope of tangent 1. But this thing is probably steep as all get. Right, ready? There's never a point where derivative is 0, so it can't ever turn. So this is a 1-to-1. Right? So it's inverted. Everybody okay, so that's good. Now I want to use this function here. I need, so this says that g prime of, in this case, a is 1 over f prime a. Oh, I'm so close, right? Because this is what I'm hunting for, g prime of a. So what I need is, oh, and of course, let me also point out one thing we could do by solving the function. That's all in function. Right, we did this example before, just take the derivative. Okay, what's the first thing I do? Start finding it. It's fine. One. How many of you are quadratic? Right, the Lane in high school. Now, I mentioned in class, there's a cubic root, right, and I actually used it. Same. Did you all know there's a reporting formula, the fourth degree polynomial? There actually is one. Nobody will ever show it to you because, I mean, it looks like crap that eating Gandalf. I mean, it's a huge mess, right? There is no fifth degree formula. And I don't mean that we haven't discovered it. I mean, it's been proven. Some fifth degree polynomials solve, some you can't in closed form. These all have solutions. They definitely have solutions, but you have to get them numerical, right? Some of them. You can't solve this. So being able to write y is up x actually explicitly find the inverse function. You want to send on something else. So I'm trying to go for this right here. Here, let's see. I wanted g prime of a, but I need a, right? So what's the goal here? Somehow, I've got to figure out what that a is. If I can figure out what that a is, then I've got everything I need. So I know the derivative. Now this, I've got no good way to tell you other than this. If we want to see the value race that we plug into this, spits out. Very good. Notice that. And I can't tell you any good way to do that other than just, I set this problem up so that something easy to work. Right? In general, this is good. Okay, now there's one more thing that worries me. Okay, everybody agree that F1 is A, so I should be able to do this. Well, what if there's another solution, right? F of 1 is A, but maybe F of -3 is A, or something like that. And then, which one do I use? This is the only solution. I found a solution, and there's no other. Can somebody explain why there's no other? The function is 1-to-1. Very good. So this is the only solution. Okay, so now let's just kind of finish it off. Let's figure out what this is. What is g prime of A? So if I want to find the slope of the tangent line, well, right. F prime of A, F prime of 1. And what was that prime? It's this thing, which is what? It's like 15, right? So g prime of A is 1 over F prime of 1, which is 1. Okay, any questions on that? Well, let's see if I can do it. That's the operative thing. I want to plug in 1 to F prime for X. Others. Okay. Any questions on this? We've got some good time left for us to talk a little bit about something called related rates. This is like the last section. So I'm going to do this pretty much exclusively on Monday as well. Now, the good news is I don't have to tell you any new math. You've got all the math that you need right now. Here's another piece. The calculus in these problems is almost always much easier than crazy crap I've been asking you, like taking derivative base. Calculus is almost always easy. The bad news is these are word problems, and it takes a lot of practice to kind of set these things up. But hopefully, but remember, like I said, you're not going to be taking derivatives, things that are super complicated. Let's start out with a problem. I toss a rock and anybody ever thrown a rock in the lake? That's a trick question, right? Everybody's done that. Splash, what happens? Right, turtles die, waves come out, right? And they come out in a circle, right? A circle circular wave expands at a constant rate of speed. Oh, you all are experienced rock throwers. How fast do you think it is when you see the waves coming out? What do you think? Like maybe 2 feet a second? 2 feet per second? We'll say that every second from where the splashdown point was, that the wave moves out. How fast is the area of circle change? When circle has diameter, let's say 20 feet. Okay, so here's the problem, right? Throw a rock in the lake, and a circle of a wave comes out. Now, this wave is a circle and it's growing, is it not? And so if the wave is coming at a constant rate of 2 feet per second, I want to know how fast the area of that circle is changing. I'm going to say radius. When the radius is 30 feet. I can see an application of this problem, right? So, for example, if you have, what happens if you have an undersea landslide, right? The ocean drops, right? And you get a tidal wave, right? Tidal wave is actually the tidal wave in the open ocean. You may not even notice it. Very small, but very, very fast, right? I think sometimes almost speed of sound. Less than that. Anyway, the speed of the wave is proportional to the depth of the ocean. So what happens is when it gets next to the coastline, the water is more shallow, and when it piles up upon itself, big disaster. Right? And so maybe we want to know how fast our radius of destruction is going to change at a certain point. So in almost every, if I made it, in fact, unless I ask you something about two numbers add up to 7, it's my product, you should almost always draw a picture of this. Now, your picture will be rewarded on the test in the following sense. If you can draw me something that, okay, I see they kind of know what's going on with the problem, I will tend to reward that with some kind of points, right? And your picture is for you though. It's not have to be Mona Lisa. Probably better if it's not Jackson Pollock, but something that will help you look and see what's going on. So here's my picture. A circle. Right? Here's dead center where I splashed the rock. Now, look at the problem here. What else might be useful for me to label? The radius. The radius seems to come up in this problem. And what should I call the radius? Should I assign value to it? How should I label that? Okay. And that's what I'm. Let me ask you this. As this problem progresses, as it moves on, this problem evolves, is the radius the same? No, it's changing, right? So be careful when you draw your picture. Anything in the problem that changes, as the problem evolves, do not give it a number. You can always put in numbers later. We'll call this R. Because the R is changing. Now, it is true that we want an answer at a snapshot, but in general, the R is changing. If you put in 30, say, instead of R, you're going to take a derivative somewhere and get to C. That's yeah. So, in fact, if you put in a letter and it's really supposed to be a number, that's a lot less harm than putting in a number for the letter. Right? So, make sure that you put in a number for something, then as the problem goes on, it's always a number. Okay, let's see. Through a rock in a lake, got it. Circular wave, got it. Rate of speed, 2 feet per second. Somebody interpret that calculus wise. What does that mean? Okay, what's it mean? Right, the rate of change, that's measured in 2 feet. Per second. This is, what is this a change of? It's 2 feet. What's change? The radius, right? So what this is saying, that it's talking to, is a change in radius with respect to time is a positive 2 meters. Right, okay? So I've got this data sort of taken care of. And write this down. It's childish, but write it down in. It's heartbreaking when I've seen students that they do all this calculus and stuff, and at the end of the day, you don't have a good feel for what you're doing. What is our quest? What is being asked of us here? How fast is the area of the circle changing? Right? So my quest is the AT. That's what's being asked. And what's relevant? DAT for all time or when? Okay, good. What is 30? Good. This is what I'm looking for. I'm looking for the change variable with respect to time when the radius is 30 feet. So you know what? This actually tells me something. Again, it's speaking to. I want the AET. I know some crap about all. I know that I want it at this point, and I know that its change is always 2%, right? This is telling me something. Say, hey, Jim, you want to get a formula that involves A and the radius. What's the formula for the area of the circle in terms of radius? There you go. This gives me crucial equation. Now, I don't exactly want A, what do I want? Well, my quest is the ADT, right? So how am I going to get the ADT out of this? Take a derivative. Well, let's DDT this thing, like Jacob Snake Roberts, and a DADT is equal to I times, what's the derivative of R squared? Are we done? 2R times 1. Remember, we took the derivative. So again, this is the chain rule. That's why we're doing the section now. We need the chain rule. Derivative of A with respect to T, the ADT, and this is 2R times the RDT. And now I got everything I need. What's R? My specific time? 30. What's the RDT? 2. And so this should be 120 pi cubic feet or square feet. Any questions? Okay, run that by me again. Because of the chain. Right. What do we come to? This is blob squared. So there's your 2 blob. Right. Now take the derivative of what's inside there. Right. And what is the derivative of R with respect to T? It's the RDT. Okay. Any other questions? Okay. Here's one. Let's see. Sand is being dumped on the floor. Apparently we're sand factory. And its coarseness is such that sand forms a conical pile with radius always twice the height. If pile is growing in height at, let's say, 6 inches. Per second, when pile is 5 feet high, how fast is sand being done? This is kind of a fascinating problem. Let me draw a preliminary picture, then I'm gonna draw a better one. I want to illustrate what's happening. You've got this pile of sand here. Being dumped on, and you can just observe that when it's 5 feet tall, it's growing to 6 inches per second. Actually, let me change it. That sounds excessive. Let's say 2 inches per second. Excessive. How fast is the sea? You can figure out what the constant volume of sand coming down is being dumped on the pile just from making that observation. Right? That's kind of cool, right. Let's see if we can figure this out. Okay. What should we do? How should we? Let's draw a picture. We draw a better shot. Okay, what's the relevant thing on life? Yeah. But as this problem goes on, is the height always, as that sand's being dumped, that pile's growing. So the radius pile, so I'm gonna label this naive with or radius and height, right? And those are variables because those are both changing as sand is being dumped. Okay. Conical pile, got that. Radius always twice the height. Huh. Can I add something in the way? So yes, I call it that's correct, but R is 2H, so I can also say this is 2H. And actually that gets me down to just one variable instead of two. So I think that's a good way to go. Everybody say, okay, so now I've got the height of my pile is H and the radius of my pile is 2H. I've used this piece. If the pile is growing at 2 inches per second when the pile is 5 feet high, how fast is the sand being done? Okay. I do see a problem, an obnoxious problem. Anybody tell me what it is? I've got a unit problem, right? This is in inches. This is in feet. Let me choose. 2 inches. How many feet? 1, 6. Okay, so all right, 2 inches per second. What is that? What does that reflect? So it says the height of the pile is increasing at 2 inches per second. Calculus in terms of my picture, my label here. What is this? What's changing? Well, that's what is changing. But another thing, it's the height that's changing. So getting our label 2 inches per second. Good. H. Actually, here's another thing that you can do. You viewers may love this. Is check your units. Right? What's height measured in? Inches, feet, something like that. And time is measured in seconds. That's the right units. Right? So okay. Let's see. The VHDT is 2 inches per second. When what? It's not always 2 inches per second. Good. H is 5. Good. And actually, I guess I should change this. for 1/6%, right? Do my work earlier. Now, finally, I think I've gotten everything that I can out of this. My next question is this: where's my quest? Where? No, something else. What is it? So what we're being asked for here is how fast is the sand being done? So what are the units on that? What region? Well, let's see. When you dump sand on the floor, what's changing? First, there's no sand on the floor, and then there's more sand on the floor. How do you measure the amount of sand that you dump? What's that in? That's a volume, right? So that should be cubic feet per second, maybe, right? So how fast is the sand being dumped? How is that reflected in my pile? I dump sand on the pile, pile gets bigger, right? What's changing? The volume of the pile. So we're asking for the VT when well, actually the DVT is constant, but we've got this in time where the volume same. Because however much that pile of sand is increasing is exactly how fast that sand is getting dumped on, right? Okay, I'm almost there. I do need a formula. So just like in the previous problem, at this juncture, it looks to me like, so I put my eyeballs on this, I got my quest, I've got a bunch of information. I need I need some kind of function that expresses the volume of a cone in terms of my parameters. Now, here's kind of a cultural question. And you'll learn how to drive all this stuff in Calc 3. I don't know what you all learned earlier anymore. I don't know. But does anybody happen to know if I have a cone, looks like this? Anybody know what volume is? Oh, good. It's 1/3 of the base times the height. And the base in this case is a little circle. Right? You will probably remember this if you do enough problems. However, if you need a formula like this, like for a volume or whatever, I will give it to you. Now, my volume here, my cone is 1/3 pi r squared h, but I can do better. Well, this has got two variables, which is noxious. It's still doable, but it's bad. But I can make this easier. How can I streamline this? So let's see. That's when 4/3 pi h. Now, let's see if we can finally answer this. Here's this is where the related rates come from. This is the formula that relates variables, and the rates is going to put the thing in derivative. You don't want these, we want the DDT. So let's DDT this one. And I get dV dt is equal to 4/3 pi. And I get to take the derivative of h cubed. What's the derivative of blob cubed? And am I done? Times the derivative, what's inside? But let me clean this up a little bit just so I can plug in numbers. Let's see, that 3 is going to cancel, so I get 4 pi h squared dh. Now let's plug in the numbers that we need. H equals 5 feet. And the HDT is 1/6, I guess. So this is going to be 4 pi is 5 squared times 1/6. And let's see. That's 106, so that's 50/3 pi. Cubic feet. That's pretty technical. Any questions? By the way, did you notice that the calculus is easy here? We haven't really taken it. We're taking derivatives of things that aren't nearly as complicated. And that's not to say there aren't some complicated things. It's not quite so bad. Okay, I want you to work on this stuff this weekend. Let me give you one to think about. A street light is I don't know, 20 feet, 25 feet. 25 feet. A 5-foot tall person is walking away from the street. At night, at let's say 4 feet. Number 1, how fast is the person's shadow how far is the person's shadow lengthening at the instant and let me also say in a straight line. So the person is walking directly away in a straight line. It's not walking in circles. How fast is the person's shadow lengthening at the instant the person is 60 feet from street light? And how fast is the tip of the person's shadow moving at that instant? How many of you have experienced a problem like this before? Ever been walking back at night from a party or something and you watch your shadow kind of grow in front of you, you walk away from the light. Anybody ever done this? Right? What's that? Right. It's just me. I wasn't walking in a straight line though. So the question is how fast is your shadow lengthening? And how fast is the tip of your shadow? It's growing and moving along the sidewalk. How fast is it moving? So see what you can do for this. First thing, draw a picture. There should be a street light and a person in the shadow. See if you can work through this and work through as many of these related rate problems. And I want to get this really hard. This is what we'll focus on Monday is trying to tweak this and fine tune. Okay, any questions?